Okay, hello and welcome back everybody. Moving on to section 5.5, the spectral theorem. It's actually my favorite section of the book. In general, if you ask me about PDEs, this is basically where I will send you to try to talk about PDEs in some sort of theoretic sense. I think the spectral theorem is kind of the best tool we have. And in fact, the spectral theorem has kind of like 6 different statements to it, depending on what sort of operators we're trying to diagonalize. In this case, we're only going to get into kind of Hermitian operators and really kind of the physicist's view of the spectral theorem for Hermitian operators. Now, ironically, this is my favorite section of the book. We're going to see in the second half of the section that we will end up having to use separation of variables quite often, which is my least favorite section. So there's a little bit of an irony between my least favorite component of PDEs with my favorite component of PDEs, just in the fact that if we ever try to find closed form eigenfunctions of some symmetric operators, it's really common to use separation of variables to try to find those. So we will end up using separation of variables towards the end. In the meantime, though, the first half, and actually I'm going to split this section into 3 videos. The first third, I should say, we're going to actually cover the spectral theorem for matrices. So it's probably not uncommon for you to have covered this in a linear algebra text. And primarily it's introduced because not all matrices are diagonalizable. That's what we want to think about here, is the spectral theorem was kind of developed to give a guarantee as to when matrices were diagonalizable. And in fact, they're a little bit stronger than that. They give a specific form of the change of basis matrices, which diagonalize any given matrix. So let's actually look at the statement of the spectral theorem for matrices, because as we encountered in the integral transform section, we should think about operators kind of as infinite dimensional matrices. And so there are some things about matrices we would like to extend. If we have nice theorems, we'd like to extend from matrices into operators. So we're going to do our best to start with the spectral theorem for matrices and see if it can kind of push us in the right direction for a spectral theorem on operators. So the spectral theorem for matrices says, let's take a matrix moving d-dimensional complex space to d-dimensional complex space. That would make it a square matrix. And you'll recall all matrices are associated to linear maps. They aren't the same thing as the linear map, but they're associated to it. And let's suppose that the matrix satisfies m dagger equals m. Let's be clear about what the dagger means. The dagger is defined right here. It's called the Hermitian adjoint. You may or may not have covered that in linear algebra course. It's defined by the complex conjugate and that's just element-wise. So each element you're going to take the complex conjugate, which just, if you recall, means you take every I that shows up and make it negative I. So m dagger is the complex conjugate and transpose. And you'll recall, transposing a matrix, you swap rows for columns and columns for rows, or you can think about it as flipping over the diagonal of the matrix. So what this is saying is if the complex conjugate and transpose, when you perform both of those operations, gives the same matrix as I started with, then we have really 3 nice statements that we can say about these sorts of matrices. So if I take a complex conjugate and a transpose of a matrix and I end up where I started, then my matrix admits, number 1, purely real eigenvalues. So if I'm going to calculate the eigenvalues of the matrix, I get purely real eigenvalues. I will never find a complex eigenvalue. Secondarily, I'll gain an orthonormal basis of eigenvectors. Now, this is the orthonormal basis of CD, the d-dimensional complex numbers. So it was a d by d matrix. And then thirdly, I end up with a diagonalization of M. So M is necessarily diagonalizable. And its diagonalization takes the form U inverse du. Normally, I would write a diagonalization as x dx inverse. This is normally how we would write a diagonalization theorem. I'm changing the language on this theorem just a little bit. And the reason I'm doing it, you'll see much later. But I'm changing the language of the diagonalization just a little bit so that we're using U inverse du. And in fact, U inverse and U are what are called unitary matrices. And what you do is you still form them. They're the same. They take the same structure as the x and x inverse would in a regular diagonalization. They're just the columns of U inverse are the eigenvectors of the matrix M. But these are unitary. And what unitary means is that it's not that the conjugate transpose, there I'm using the dagger again at the bottom. The conjugate transpose is not the same as the matrix itself. It's now, with a unitary matrix, the inverse matrix. So you can think about unitary as defined by having the inverse is the same as this dagger, which is the conjugate transpose. So you can imagine it like that. And this U inverse is defined by the columns of eigenvectors. And then, as always, in diagonalization, the diagonal matrix D, all of the diagonal entries are diagonally with the associated eigenvalues. So every eigenvector here has its associated eigenvalue piece by piece. Now, people always ask me, does the order matter when it comes to diagonalization? The answer is no, so long as you make the pairings correct, right? So these two numbers have to be paired together. These two numbers have to be paired. These two have to be paired. So as long as you pair the correct column, being the eigenvector, along with the correct associated eigenvalue in the diagonal matrix, the order doesn't matter. It's just that, if I swap two columns, then I have to swap those two diagonal entries in D as well, so that the eigenvalues and eigenvectors still line up. But that's what the spectral theorem says. It says, hey, if I have this special class of matrices called Hermitian, then I necessarily can diagonalize them, and I have better properties in that. The diagonalization necessarily has purely real entries in the diagonal matrix, and the change of basis matrix is what's called unitary. So we get really strong properties out of the diagonalization of these so-called Hermitian matrices. And the proof I just sent you towards any linear algebra text. The proof is fairly straightforward in a linear algebra text. So now what we're going to do is try to extend this notion of a Hermitian matrix into a Hermitian operator, right? We want to think about, what is this notion of the M dagger being M mean? What it means for a matrix actually is that if you take the matrix times a vector, you take the inner product against another vector, it's equivalent to moving the matrix over to the second vector. So in other words, a Hermitian matrix is one in which it doesn't matter which x vector or y vector the matrix hits before computing either mx dot y or x dot my. These will give the same answer. So that's the definition of or it's an equivalent definition to a Hermitian matrix. And it's useful because that definition is a lot easier to extend to operators. We don't really have a notion of transpose. We maybe have a notion of complex conjugate on an operator, but certainly not a transpose of an operator. What we have instead is this notion, where as long as I have an inner product space, right, some sort of well-defined inner product on my, I'm calling it a vector space here. You can also think about it as a function space. Function and vector spaces are the same. So as long as I have an inner product on my space, we call a linear operator L Hermitian so long as it doesn't matter which term in the inner product the operator acts on. So it could act on the left-hand side of the inner product or the right-hand side, and I necessarily have to gain an equality. This is the definition of Hermitian. So let's actually see that in a nice example. So everybody's favorite example, at least when you leave a PDE's course, should be the Laplacian. And this is, we're going to define the Laplacian on the space of test functions for this round. Or we're going to note that that is a symmetric operator, at least on the space of test functions. So let's just recall what the space of test functions in. We originally encountered that in section 5.2, the Dirac delta function. It's kind of the natural space the Dirac delta function acts on. So the space of test functions is going to be the space where all of the derivatives exist, and in fact all of them achieve the value 0 on the boundary. Okay, we're going to see that the Laplacian delta is going to be symmetric here. Well, to be symmetric, let's look at our definition again. We really need a notion of an inner product. It doesn't make any sense if we don't have an inner product on the operator's domain. So we ask ourselves the question, what is the natural inner product on the space of test functions? And it's not too hard. Kind of all inner products of functions look the same. So they're going to look like the integral over omega. This is the domain of the functions. So we're going to integrate over the domain. We're just going to multiply the two functions together. This is really the inner product on all, maybe I'll say up to scaling. A lot of function spaces will have different scaling parameters. They'll maybe normalize the set, but that's really the inner product up to scaling of, put it in quotes, all function spaces. And so if you're curious when you have an operator and you're asked to prove that it's symmetric over some function space, and maybe for some reason the author hasn't given you the definition of the inner product, you should always think about it as the one that I've drawn in the middle of the screen here. So that's going to be your inner product. And all we want to do is we want to test this property underneath that inner product where L is delta. Okay? So in other words, what do we want to show? We want to show that delta F G equals F delta G, but that's kind of a fairly obscure way to write it. So what could I do instead is really we want to show that the, I'm going to use this definition, the inner product now. So we want to show that the integral over omega of delta F against G is the same as the integral over omega of F against delta G. Right, so there's some notion where I've pushed I've pushed delta from acting on f to acting on g, and ideally those are the same. You could definitely imagine a lot of situations where it shouldn't be the same, depending on which functions we're utilizing. But really, this kind of looks like an integration by parts problem, right? So symmetric operators are kind of like the ones with which integration by parts works really, really nicely on. So we're going to try to show that. It's not too bad to show it as long as you remember your calculus 3 with Green's identity. We've already encountered it once. We're actually going to show it a little bit differently because Green's identity states this entire term here. It says actually that if you subtract the inner product of, that's really the inner product of delta f against g, and then you subtract the inner product of f against delta g, that gives you a really nice integration by parts formula where you only have to integrate over the boundary. But the important thing about the test functions, right, what do I know about test functions, is that the value they take on the boundary is 0. So since that's a test function, and that's a test function, the value it takes on the boundary is 0, meaning that this is 0, because test functions. Okay, and that's what I've written down here then. So because of Green's identity and that we're working over test functions, we have really that the subtraction of one inner product against the other inner product is 0. What does it mean to subtract two inner products and give them 0? It means that each inner product must be equal to the other one. So the inner product where you act the Laplacian on f and then multiply it by g is the same as taking f and multiplying by the Laplacian on g. So that's what it means to be symmetric for an operator, as long as we can show that property about the operator with respect to inner products. We also have to cover kind of the other topics that are included in the spectral theorem for matrices. We have to cover what does it mean to be unitary, what does it mean to be diagonal. So we're going to try to encounter those in some sort of infinite dimensional or operator theoretic sense. And we have it here in the sense that really unitary means that if I take the dot product of two vectors, it's the same as taking the dot product of their image under the unitary map. So the inner product of two vectors is the inner product of their image under a unitary map. That's kind of the definition of unitary. We're going to think about, okay, you map them somewhere underneath this matrix, both of them. As long as that inner product remains unchanged, that's what it means to be unitary. And so once again, in function spaces, when we have a notion of an inner product, we have a similar notion of unitary. We're not going to think about having this weird complex conjugate transpose notion, because that's a lot harder to talk about. But what we can talk about is the inner product of two vectors being the same before or after a unitary transformation. So a unitary transformation is a linear map. Those are perhaps different vector spaces. We're going to see in a lot of cases they're definitely different vector spaces, but they both have inner products associated with them. That's what the subscript is describing here. So two vector spaces, maybe they have different inner products associated with them, but a unitary map leaves the inner product, I should say it's the inner product's value, right? The inner product itself is changing, but the value it takes unchanged. So as long as you pay attention to where both x and y end up after you take u, as long as that value remains unchanged, we call it unitary. So we'll look at an example of a unitary map here. The Fourier transform is the one that we like to bring out right away when we talk about unitary transforms, at least on infinite dimensional spaces. So we can think about either the Fourier transform or the Fourier series transform. You'll notice that the second example is the series transform. So they both kind of work. Over an unbounded domain, RD, the Fourier transform is a little bit easier to understand because in this case, the space that the unitary map maps us between, right? U is going to map us from V to W. It's actually the same space. So for the regular Fourier transform on RD, U doesn't really change the space, or I shouldn't even call it U because this is actually the Fourier transform F. That's going to be a unitary map that kind of keeps the space the same, but we want to check and see that the inner products remain unchanged. So this is kind of important, right? So we're going to check the difference between the inner product of two functions in L2, and then we're going to check about the inner product of the image of both functions under the Fourier transform. So the image of both functions under the Fourier transform. And in fact, the fact that these inner products are equivalent, or this fact, it's the same sort of thing. This was Parseval's identity or theorem, or sometimes it's called the Plancherel theorem. If you go back to lemma 2.3.2 in this text, that states that this is actually true. So kind of the Parseval's identity was the original proof that the Fourier transform was unitary. And then actually this was kind of developed before we even really knew what it meant to be unitary. People were aware that, the Fourier transform satisfied that property without necessarily giving it a nice name. But that's Parsifal's identity for you. And in fact, you can extend Parsifal's identity to the Fourier series transform as well. This is kind of the more interesting setting though, because when it's a Fourier series, the domain and the codomain of my unitary operator U are different, right? So L2 of the d-dimensional real space is different than little L2 of the d-dimensional integers. Don't really worry about what this is. We've already defined it in chapter 2. So go back to chapter 2 and just see what the image of this Fourier series transform is, and you'll be able to figure out what little L2 of ZD is. But that's the kind of the codomain, the domain and codomain of the Fourier transform, at least for a bounded domain. And actually I'm noticing a typo here because this should actually be the d-dimensional torus, right? Not the d-dimensional real numbers. So that's what gives you the Fourier series. It's when you start with the d-dimensional torus instead, and I should actually, I have typos abounding there. It should be the torus as well. Once again, go back to chapter 2 if you forgot what the torus looked like. Chapter 4 actually, for the torus. But the Fourier transform, when it's the Fourier series transform, is also going to be unitary, and it's the same reason, which is Parsifal's identity over the Preliminaries theorem. You can show that fairly straightforward. And then finally, we want to talk about what it means to be a diagonal operator. There's not really the same sort of notion of a diagonal matrix when we're talking about operators, right? Because you don't have a matrix representation necessarily, but a diagonal operator is going to now have the name multiplication operator. Okay, so we're going to assign this thing the name multiplication operator. I still use the label capital D sub h, so you want to be careful with that. A lot of people will use capital D's for derivative. In this case, this is not a derivative, but quote unquote diagonal. That's why I use the capital D for multiplication operator. It's really a diagonal operator. And this is just any operator which takes the form when it acts on a function, it acts by multiplying by another function. So we've got some other function h, which just multiplies f, and that's why it's called a multiplication operator. So that little multiplication there is the name multiplication operator. Now it may feel strange that this is what it means to be diagonal in an infinite dimensional setting, but let's see why. So I'm going to jump back to a finite dimensional setting and give myself the very, very contrived function space V. I'm saying I'm taking functions from the set 1, 2, 3, and we're going to output a real number. So the input to every function is just the three numbers, 1, 2, 3, and it's going to have some output in R. So let's look at an example of one of these. Maybe call it H in this space. It maps, so n, when n is 1, we're going to give a 3. When n is 2, we're going to give a -2. When n is 3, we're going to give a 1. So this is a perfectly allowable function in V, and we're going to define a multiplication operator, d sub h, corresponding to this particular function. We're going to act it on an arbitrary function. So by definition, the multiplication operator has to multiply f by h, which means it multiplies whatever number f1 takes, whatever number f2 takes, whatever number f3 takes, it exactly gets multiplied by the value of h. So h is just going to multiply f1, f2, and f3 by its inputs, 3, -2, and 1. And so you can write kind of the operator in image form right there. That's the image of the operator. It's just 3 times f1, -2 times f2, and 3 times f3 for whatever values f1 and f2 and f3 may take. So we look at a specific example of the multiplication operator acting on the function g, which I'm defining as -1, 0, and 2. And we look at dh on g. Well, that's the same as multiplying g by h. So we have 3 times -1, -2 times 0, and 1 times 2. So we get -3, 0, and 2. Okay, so we can define everything here just in pure function form. This is pure function and operator definition. But really, this has been contrived because every time I'm writing these down, look at this. That looks exactly like a vector, -1, 0, 2. F looks exactly like a vector if you look at it like that, f1, f2, f3. And so what's going on here is that the diagonal matrix, whose entries are exactly h1, h2, and h3, corresponds exactly to the multiplication operator, which is multiplication by h. Okay, so diagonal matrices and multiplication operators are in fact the same. I can show this here by actually writing G as a vector and performing the matrix multiplication of H on G. You exactly get the image that you would expect, right? That -3, 0, 2 is right here. It's the same one we got earlier. So multiplication operators are actually just diagonal matrices. We just happen to have infinitely many entries to them, so it's not really quite so clear that we can write them in a diagonal setting. So that's our version of diagonal. Just scroll back up to it once again. Multiplication operator is our version of diagonal. And we're going to encounter, I'll just give you an example of one other multiplication operator here, d sub x. It's a very common one and one that will be very important very soon. D sub x, as long as it's multiplying f of x, just multiplies f of x by x. That's going to be a very important multiplication operator for us very soon. So to kind of conclude today's, because I don't want to get too much into the spectral theorem, that will be the target of the next video. Let's just keep in mind that we have a spectral theorem for matrices where we have n is u inverse du. We want a spectral theorem for operators. Maybe I should make this clear. It's a spectral theorem for Hermitian matrices. And we want one for Hermitian operators. Now we're going to have L is u inverse du, where d is a multiplication operator, and u inverse are going to be unitary operators. So that's where we're headed. That's why we've developed everything we have developed in this video. So just look forward to a statement of that in the next video. I'll see you then. Bye.